While Gaussian elimination is a perfectly good way of producing the row echelon form of a matrix, it almost always requires us to work with fractions. Fortunately, we can avoid using fractions using an ancient Chinese approach known as fang, cheng, which translates roughly as rectangular tabulation method. And this works as follows. Given whatever row we happen to be working on, we'll multiply all of the other rows by the pivot, and then we'll add multiples of the working row to these other rows. So let's see how this works. Let's go back to that awful, painful problem that got us those horrible fractions. But this time, let's try and redo this problem using the fang, cheng, method. So let's go ahead and set down our augmented coefficient matrix. Since we're already in standard form, that's just a matter of transcribing the coefficients and constants. The first row has pivot 2, so we'll multiply all the other rows by 2. So our first row remains unchanged. The second row was 3, 0, 2, 5, so if we multiply it by 2, we get 6, 0, 4, 10. And the third row, 5, 2, negative 1, 6, can be multiplied by 2 to get 10, 4, negative 2, 12. And again, these new rows replace the original rows. So we don't need to keep the originals anymore. Next, I'll add multiples of the first row to the others so I can get zeros below the pivot. And because we multiplied every other row by the pivot, then the leading coefficient of every other row is going to be a multiple of the pivot. So if we take a look at the second row, we see that if we multiply the first row by negative 3 and add it, that will eliminate the leading coefficient. So we'll multiply the first row by negative 3 and add it to the second row, and that'll give us a new second row, 0, negative 9, 1, negative 8. And since we have this new second row, we no longer need the two rows we added to produce it. Likewise, if we take a look at the third row, multiplying the first row by negative 5 and adding will eliminate the leading coefficient. So we'll multiply the first row by negative 5 and add it to get a new third row, 0, negative 11, negative 7, negative 18. And again, now that we have a new third row, we don't need the two rows we used to produce it, and we can eliminate them. So we'll write those down, and we don't need the others. Since we have zeros below the first row pivot, we can move on to the second row, where the leading coefficient is negative 9. So we'll multiply the following rows by negative 9. So that will give us 0, 99, 63, and 162. And we no longer need the original third row. We can replace it with this new third row. Then we can add a multiple of the working row to get zeros below the pivot of the working row. In this case, if we multiply the working row by 11, we get 0, negative 99, 11, negative 88, and adding that to the third row gives us 0, 0, 74, 74. This gives us a new third row, which along with our first and second rows give us our augmented coefficient matrix in row echelon form. And now that the matrix is in row echelon form, we can use back substitution to solve for all the variables. So the last row corresponds to the equation 74z equals 74, which we solve z equals 1. The next to last row, negative 9y plus z equals negative 8, we can substitute in our value for z equals 1 and solve for y. And finally, the first row corresponds to the equation 2x plus 3y plus z equals 6. We'll substitute in our values for y and z and solve the equation for x. While we won't be able to avoid fractions forever, we can delay their onset for quite some time, as this example shows. So we'll start with our augmented coefficient matrix. The first row pivot is 2, so we'll multiply the other two rows by 2. So if we multiply the second row by 2, we get 6, 2, 4, 2 as our new second row. And if we multiply the third row by 2, we get 10, 6, 0, 6 as our new third row. Now to eliminate the entries below that first row pivot, we can multiply the first row by negative 3 and add it to the second row. Multiplying the first row by negative 3 gives us negative 6, negative 9, negative 3, negative 21. Then adding these entries to the second row gives us 0, negative 7, 1, negative 19, which will be our new second row. Similarly, if we multiply our first row by negative 5 and add it to the last row, we'll get a new third row. So multiplying the first row by negative 5 gives us negative 10, negative 15, negative 5, negative 35, and adding it to the third row gives us 0, negative 9, negative 5, negative 29, which will be our new third row. And this is the first step in our row reduction. Now we have zeros below the first row pivot, so we'll move on to the second row, where the pivot is negative 7. So multiplying the following rows by negative 7, that gives us 0, 63, 35, 203 as our new third row. Now if we multiply the second row by 9 and add it to the third row, that will eliminate the entries below that second row pivot. So multiplying the second row by 9 gives us 0, negative 63, 9, negative 171, and adding it to the third row gives us 0, 0, 44, 32, which will be our new third row. Now you'll notice one of the disadvantages here is that the numbers in our matrix grow larger and larger, and this is the price we have to pay for avoiding fractions. However, every now and then we find a row where all entries are divisible by the same number, and so it's convenient to remove any factor common to all terms in a row, because this will help prevent our numbers from getting too large. So here we'll multiply that third row by 1/4 to get 0, 0, 11, 8 as our new third row. And now our matrix is in row echelon form, and we can solve using back substitution. So beginning with the last row, which corresponds to the equation 11z equals 8, we can solve that. Z equals 8 elevenths. The next to last row corresponds to the equation minus 7y plus z equals negative 19. We know the value of z, so we'll substitute that in and solve the equation for y. The first row corresponds to the equation 2x plus 3y plus z equal to 7. We'll substitute in our values for y and z and solve for x. And so this gives us our solution. X equals negative 12 elevenths, y equals 31 elevenths, and z equals 8 elevenths, which we'll write in vector form.